So my name is Hinojosa, and we're going to talk about machine learning data pipelines today. All right, so as far as machine learning applications, lots of different things that we could do, like fraud detection, financial approvals, get a credit card application or something like that. Picture recognition, although that does come with some, legal implications, particularly when your civil rights are threatened. Picture recognition could be some, but depending how you want to use it, and your idea here. So we've seen the advent of ChatGPT, and it's going to be pervasive from here on out. So if you don't have any kind of machine learning within your particular business at this particular time, it's going to come up here really quick. All right. So the process of machine learning, let's go ahead and talk about that. So this one is from a book called Doing Data Science, and this shows the process for doing any kind of machine learning. We have raw data is collected from the world. That particular data could be, good, could be old, could be inconsistent, could be missing values. How do you go about doing that? You then process the data, clean the data, just because not a lot of things are perfect when it comes to your data. So you would have to undertake, any kind of cleaning. And by the way, all these slides, and this is actually I do a full day workshop of this same one. So if you want to take pictures with me next to my slides, hey, that's cool. But these slides are also on a GitHub. If you want to see me afterwards, I'll go ahead and bring up that particular GitHub, and you can take a picture of it. All right. So we get the data, we prepare the data, we clean the data, and then we need to explore if everything is going to be correct. Now you'll notice here this exploratory data analysis arrow kind of goes back to the raw data is collected. We need more data, and we need to capture that data and start to ingest that again, and get better data over and over and over again. Then it's machine learning is not about just like, hey, let's get a machine learning algorithm, let's plug data into it. It's about looking for the right one, making sure your data is correct, and then feeding that into the machine learning algorithm of your particular choice. But also, if you take a look down here at the bottom, it's about visualization as well. What kind of data are you looking at? Put that on an XY graph, or put that on an XYZ graph. See what you find. Are you looking at blobs? Are you looking at lines? What is it that you're looking at? And then you're going to build up a data product. And so once you have this data product, it's going to be like a first round. It may not even be that great, but then you mature over time, because it's going to be a cyclical process. You build a data product and you unleash that on the real world with real data. Okay. Anybody here do machine learning now? Okay, 1, 2, okay. So some of you already know this. The way the machine learning works is very much like if you were doing any kind of study. Let's say a calculus exam or a physics exam or any kind of exam that you've undertaken, where you have a book and you look in the back of the book for the answers as you're studying these sort of concepts. So machine learning models work in that same kind of way. So for example, like training would be, here's the data, here's the target, which is the answer. This one's called supervised learning. And you can give that into the machine learning model, and that would be called the training phase. So you decide, what the answer is going to be. So this would be like the risk. And so this is a heart event. Are you at risk of a heart event? And what things are going to lead, to this particular heart event? Well, you could have some columns, and you see over here on the slide, I have ID, age, sex, and blood pressure, and as well as the risk on whether they're going to have a heart event or not. So one of the things as far as like data engineering goes and finding the correct data and using the correct data, you're going to take a look at this and you're going to see the columns. And one of the things you'll notice here is that ID is it's an identifier. Should we keep that in? No, well, let's remove that. Because you could build up a superstition when it comes to machine learning. So you don't want the situation of, hey, what are the last two numbers of your social security number? And it's, 57. Ooh, that's a terrible number. I'm sorry, you'll probably have to go see your doctor about your heart. Like, what? That doesn't make sense. Like, what would your social security number have anything to do with? So nonsensical stuff over there on the ID. But then we have age could be relevant, gender could be relevant, blood pressure could be relevant. Maybe I want to remove gender. Maybe it's not, a good statement of data. Maybe it is, and maybe it isn't. So data scientists have different words than, let's say, data engineers and programmers. So the columns here are going to be called features, and the rows are going to be called observations. So a data scientist will do this sort of thing of like preparing the data. So, splitting up some training, about 60-40 or 70-30, splitting up the training, splitting up the testing to, go for one round with training, the other round with testing. Perhaps a better idea would be randomly distribute what you're going to choose for training, what you're going to choose for testing. And again, very much like the way that we've studied in school. I looked at a problem. I'm going to look at the back of the book after I made an attempt to solve that problem. Did I do correctly? No. Right? And then you try to do it again until you get better and better and better at it. Same sort of thing is happening here. The machine learning algorithm is going to take that particular data. We're going to have our model. It is going to take the training data. It's going to feed off of that training data, come up with some certain conclusions. And then what we're going to do is very much like your teacher in school. Let's put this in the back. We'll take the actual answer and we'll put that in the drawer, lock it up, and then we'll give you a test, exam time. So how well did this model do? Well, I'm just going to feed you the testing data, and here we go, and this is going to generate a result. And what we're going to do is very much like our teachers did, unlock that drawer, take that little answer sheet out, take the red pen, and let's take a look at how well you did. So how did we do? So we'll take that and take these two bits of information, and let's do a comparison of it. And that's the idea of machine learning. So go and be fruitful with your machine learning models. There are classic ones like k-nearest neighbors, naive Bayes linear regression. On the deep learning side, this is where we have our neural networks. And there are different kinds of neural networks that could be used for different purposes. Now, one of the reasons why I wanted to create this as a workshop and why I wanted to create this as a presentation is that, our modern look into our jobs and what it is that we're doing is going to be divided up. In fact, my opinion is that our world today, as far as programmers or engineers, is divvied up. It's kind of like your family doctor knows a lot, but at some certain point you have to go to a specialist, right? Same sort of thing. And so that's what we see here. Now, should everyone know data science? Should everyone know machine learning? Absolutely yes. I don't even consider myself a data scientist. I'm, very novice on the machine learning side. But every programmer should know machine learning and what is involved and what data scientists do. Because there's a role and responsibility that is being done for making sure that machine learning models are deployed and done so correctly. So we have data engineers here on this graph. We have data scientists and researchers as part of this graph, and we have machine learning and production engineers. So the data engineers is the historical streaming side of the information. How are we ingesting this data? Historic is like, hey, let's go to a big old data store that we've been collecting information over the years and let's do something with it. Streaming is the moment something happens, we want to do something and munge and transform that data the moment that it's happening. That's the difference here between the historical and streaming. But a data engineer would have to provide all this for the data scientist, which is the next set of items, where they ingest the data because the data engineer makes that available and should do a good job of making sure that it's very well cataloged, know where that information is so the data scientist can start to use it. So they will ingest the data. They will visualize it, again, graphing it, see what they have. Feature transformation engineering, I just mentioned what a feature is. Those are going to be the columns in your data. Find the good model, evaluate it. It may not be the wrong one, but continue to try different models. So that's what the data scientists will do. They'll come up with a particular product. Then this is where the production engineers will then take over, where they will deploy that. And the important part under this deploy arrow is pipelines, not just models. And they will also need to version it, because maybe we're going to do a terrible job this next time around and we need to go back to a previous version. And then at that point, we can then go into the live system. But once we go live, monitor. So this is where a term has been coming up called MLOps, the combination of machine learning and operations. Kind of an empty field right now, and I don't think there's any kind of, quite perfect candidates at this particular time, because we either are good at the CI/CD operations side of things, or we're really good at the data science sort of thing. And so I think this is going to be a land of great opportunity, if you will. So why the need for communication? Here's the thing. And I know there's been some talks, or I've heard there has been some talks on doing machine learning in Java, and while certainly that is a possibility as well. Data scientists, Python. Anybody here do Python? Okay, well, that's a good number. All right. And then, Java for the data engineering stuff is likely going to be a JVM-based language, but, may very well be like Java or Kotlin or any one of those. All right. So over here I have the Dean Wampler architecture. Dean Wampler is an excellent author, speaker. He was doing this talk a few years ago, and I saw this image here, and I'm like, please, let me use this particular image here. And hopefully you could see that. Oh, that looks nice and big there. So what is this Dean Wampler architecture? It's just a sample architecture. You don't have to absolutely adhere to it, but I thought it was fantastic. Now, if you take a look here, I have 1 through 9. 1 is getting data into the Kafka cluster, which is going to be your data backplane. We have REST calls made to Kafka. The Confluent stack has something called a REST proxy that is front-facing in front of the Kafka cluster, which could take RESTful calls and translate that into messages. But you have your microservices, your Spring, your Node.js, your Quarkus, or whatever you would like. And data comes into this particular data backplane. This serves as a big, gigantic buffer for your business. Messages will go into that Kafka cluster. And then the important part here is going to be number 6, where I have Akka streams and Kafka streams. I'm going to talk about Kafka streams in this particular presentation, where the job here is take a message off of that particular broker or particular pub sub, take a message off of it, take it out, do something with it, and then feed it right back into Kafka, but under a different topic. So Kafka does things as far as topics, which are going to be analogous to database table names. Now, the other stuff are just some other things that you could do, like Spark can do mini batch processing, can do full batch processing. You'll notice the number 9 there is getting information in and out of long-term persistent storage. One of the greater aspects of this is also number 5, which is Kafka Connect, which is once a message arrives into Kafka, you can take that information, ingest that, and then put it into your favorite data storage. But if you notice there, number 5 is also a bidirectional arrow. So you can take information from Kafka, store that into the storage, or go the other way around where you have storage, like maybe you have an old MySQL database, but even Kafka Connect, you could also do like message queues as well. And let's go back to the classic style database. Someone enters a row into a particular table. Well, Kafka Connect will do this kind of listening and, oh, hey, there's something new there. Right, let's go in and take that information and make it into a message. So there's this whole evolving ecosystem that I'd like to put in play when it comes to these machine learning data pipelines. And here's a more simplified of taking that Dean Wampler architecture and just making it a little bit smaller. So the idea here is microservice, report to Kafka, send information to Kafka, where we can do real-time data analysis as it arrives in Kafka. And I'd like to use Kafka streams to communicate with something called TensorFlow serving. TensorFlow serving is going to be the fully trained model that we wish to deploy, okay? Redis I'm going to use as a key value store, and not that I have anything against Redis. I think when I was done with this particular workshop example, I was thinking, oh gosh, you know what? I could have totally used Kafka as a key value store, but I chose not to on that one. But it's fun anyway. So we can post information to Kafka, and again, we could use Kafka Connect to post to Kafka. We can have a producer, we can have a REST proxy that posts to Kafka. And as far as Kafka and streaming, we can get information from Kafka, do something with it, do some sort of transformation, and post that. This is what's called a consumer-producer pattern. As I consume information from Kafka, I'm going to do something with it and produce it. Now, a stream application or KSQL DB does that behind the scenes. It's already engineered for you, so you don't have to think about the hard stuff. And that's where KSQL DB comes in. I can ingest something, but let's propose on this that as this KSQL DB is ingesting information, I want to do something with it. That one thing, that something that I could do with it is give it to a machine learning model to do a prediction, something that has already been done by the data scientist, and it's already been prepared and it's already in production. Do my classification for me, and whatever that classification is, I want to feed that back into Kafka. And that one's called KSQL DB. It was once called KSQL, so if you're looking at the diagram there, it was called KSQL. It's now called KSQL DB because you can just set up databases immediately with it. So lots of different things that you can do and lots of different ways that you can go about it. You can have KSQL or KSQL DB along with your TensorFlow to make a prediction. One of the cool experimental things that I can't wait for is how far GraalVM is going to take its Python stuff if indeed you're going to be running this in Python. So there is a Graal Python that you get with GraalVM. And the goal there would be like, hey, can you do scikit-learn, and can you use a whole host of different kind of Python libraries? Because again, the data scientists prefer their Python or their R language. So the one I'm going to show you today is, hey, I'm going to get an input, and I'm going to use a streaming application to ingest the information from it, call TensorFlow as a separate microservice, get that request, get the response back, and then go ahead and do my prediction. Now, one of the other things that I just wanted to mention here, how we can translate models, and this is just an aside thing. There are lots of document formats because a model is done mathematically and there are hyperparameters, and you could describe all that information with different kinds of documents. So as another solution, you could take a document and say, this is the neural network that I did, and here are the hyperparameters that I used to create that. And you can enshrine that into a PMML, which is a XML-based standard. So I can go from one language or one framework and say, here's the model, can you go ahead and run that in production? Another one's called PFA, portable format. This is JSON-based, but you can tell here by the diagram, you can have scikit-learn, you could have R, and then transform that or transfer that into other frameworks like Spark. Another one is called this one, Open Neural Network Exchange, ONNX. That one's a Python API-based one that you can take a particular model and output it. H2O.ai has Pojo-based modeling as well. I thought that was kind of interesting. All right, well, let's see here. Just taking a look at the time here. I'm going to just briefly talk about tensors, just so that way we can take a look at the document and how to start productionalizing something in TensorFlow so that way we could start to make our particular web service. So I may skip some slides for this because I'm just gauging the time right here. So we can have a scalar, it's called rank 0. We could have a vector, which are two numbers that represent something. We could have a matrix. I think we all know what a matrix is. But a tensor is a mathematical entity. You could think of it like a matrix of a matrix and a set of those. But if one transforms, then the other entities must obey a related transformation rule. So one way to think about like what a tensor is, and it's probably incorrect, but if it helps, it helps. And that is like Sudoku, where you do something over here due to a mathematical transformation, you're going to have to change something up on top. Okay, so just a neural network, just an explanation for this, just in case you have not seen that before. You have inputs, which are on your left-hand side. We have outputs. So one of the things that, as far as inputs could be is like, what's the dew point, what's the temperature, what's the cloud cover, and what's the humidity. And given those 4 factors on the left-hand side, how much cloud cover do we have? What's the temperature? Is it really high? Is it really low? Maybe that doesn't even matter. But I'm just making an example here. Those are going to be the inputs. And then on the output, in this particular case, maybe I want to determine, is it going to rain or not? Okay? And then I could have what's in the middle. Those are going to be called inner layers. Okay? And each one of these are neurons. Okay? And they're all tied together. And what they do is they activate. So based on some sort of input, and again, I could have like 100%, maybe that neuron's going to be like turned on really high. Some are not, some are going to be kind of like partway there, but it's somewhere between 0 and 1. And then at the end, I get what's called a probability. So if it's a rain, maybe the top one's rain, the bottom one's not rain, they should all equal to 100. So all starts here on the input, and then the inner layers are going to be what are called activation functions. They're going to be activated. They're going to start to get excited, okay? And that's where these activation functions will come in. There are lots of different ones. 10H, ReLU, CLU, leaky ReLU. They sound like Teletubbies, let's be honest, but they're all like mathematical formulas that are going to activate. One of the more modern ones is this rectified linear unit, or ReLU. So they had used a sigmoid, which is kind of like an S-curve, but the problem with an S-curve is like after a certain point, it always becomes 1 or it always becomes -1. In this case, the rectified linear unit just continually grows and grows. So if you have a neuron with like some sort of heightened experience, it's going to be like, yeah, I'm really excited about this data. Hell yeah, that's the sort of thing that you're going to get with a rectified linear unit. So these neurons just go boop, 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 boop. They start getting excited about things. So let's say that, let's see, what do I want to do? Let's say that I want to draw, let's say I'm pretending to draw a square. I didn't think about this one. I usually do this on Zoom and I have my little marker, but I'm like, where's my marker? Anyway, let's say, I don't know if you can see my little arrow there, but let's say that I have an arrow and I'm going to draw a box on the upper left-hand side of this. Okay? And I'm going to assign that to one of you, and that's going to be that particular neuron that you're going to either be excited about or not excited about. And if you're just the one that's just looking here in the corner, if there's nothing but white space here, you're going to be the neuron that goes, right? If you're looking at a pullover, right, we're going to have you're going to have a lot of information here. So for that neuron, you're going to be like, yeah, look at that, woo, okay? If you're looking at a square over here, maybe you'll get a little bit of that edge over here on the right-hand side, and you'll be like, oh, all right, I'm pretty excited about it. Maybe I'm like 10% excited about it, right? So over time, you're going to end up learning as a neuron, hey, you know what? I get really excited about coats and shirts and shirts, or coats, shirts, and pullovers. Sorry, there we go. I get really excited about that because of that neuron. I'm looking at that particular space and I get excited about stuff. Maybe for pants, how about this? I see something in there. This is from the TensorFlow website, but I'm taking a look at, hey, I see some dark edges around here and then a white space in between. I'm going to get excited about that. So there are, certain things that a neuron is going to be assigned and is going to look for. Now, let me come back over here 28 by 28 is 784. I was going to create 784 inputs on the left-hand side, but I got lazy. And also, my presentation software didn't like that very much and started crashing. Anyway, so let's pretend I have 784 inputs here on the left-hand side. Things are going to be coming in, and then the inner layers are going to be just the excitable ones. They're going to be assigned a portion of this image or whatever it is, and they're going to go crazy or not crazy. So some of these, are not going to be interested in the inputs that you're going to be receiving. So the way a neural network works is you're given weights on each one of these neurons. So if you're a neuron that goes, yay, yay, right, and it acts constantly and it gets excited about things sometimes, but then goes really low. Well, I need to hear from you, right? So a weight is going to be, something that you can turn on for a particular neuron, just like really get excited about. So that's what a weight does. We want to, bring this down into like 0 or 1 space. So what we're going to do is we're going to apply a sigmoid function. As you can tell here, this one is, this one's between 0 and 1, S-curve in this particular image, but we want everything around that particular space for 0 or 1. So we'll put that in a sigmoid so that way we can smush it within that particular space. And then what we're going to do is we're going to attach a bias to it. Okay, so it kind of gives you an idea of what it is that we're doing there. So bias is just a way to make it a little bit harder to activate. But that's what the idea about, a neural network. Now, so I just wanted to tell you a little bit about that and how that works. I'm going to come in over here, and what I'm going to show you is this particular Reuters data set. So this is the Reuters data set. This one I took from a very excellent book called Deep Learning. Deep Learning with Python. I couldn't see the word with, by Francois Chalet. A very excellent book. I like that one a lot. There have been, with my studies, I've been trying to pick up, as many books as I can. One of the things that really drove me nuts were like the books that were talking about like brain neurons. And I'm like, that doesn't help me. This one didn't do that, and this is why like that book is always going to be and have a great place in my heart, because it's just like let's just jump right into it. Anyway, how many of you have used a Jupyter notebook or a Jupyter lab? That's a good substantial number. So the data. How many of you used like a Jupyter lab with Java? Has anyone done that with Java? No hands there. Well. Pythonistas love their Jupyter notebook. How many of you use Jupyter Lab instead of a notebook? Just out of curiosity. Wow, interesting. So that was like 0. Whether you're doing a Jupyter notebook or a Jupyter Lab, this is the place for a data scientist. This is what they absolutely love to work with. One of the reasons is a data scientist is able to tell the story. So this is the place that they work in. And so what do I mean by telling a story? I got data from here. The reason I got it from here is because of this, right? I'm explaining myself. And through that explanation, I get to put in text and I get to put in code. Well, here's a little bit of TensorFlow to give you an idea. So this is TensorFlow as TF. I'm getting a data set, and these are like newspaper articles. And what we're going to do with this one, and this is going to be, let's get 10,000 inputs of the more common words, and let's put that as the input. And then at the end here, I am going to determine 0 through 45, which is the classification called multivariate classification at the very end. So in other words, a newspaper article could be about earnings. It could be about aluminum or oilseed or gold or tin or whatever it is that you want to classify that as, okay? So in this particular document, I have like get a word index, which is a number because machines don't read English. They read numbers and understand numbers. So, everything in here is going to have a corresponding number. So if you decide to go to ML, in the field of ML ops, one of the things you're going to need to know is how the translation occurred if you're dealing with words, and there are a lot of things like that that you would have to look to and understand. So here I'm outputting that to a JSON file. And we're going to convert things into numbers, but here's the decoded version of that. So this one says, grain trader said that they're still waiting results of yesterday's UK intervention, blah, blah, blah. Okay, but what we want to do is we want to prepare the data, and in this case here, what we're doing, like what's this big thing here? This is 10,000 elements. That's the entry that we're plugging into the model. If the word is in the article, we're going to flip that one on. If it isn't, we're going to keep that one at 0. Labels are the answers. So this 3 represents one of the classification from one of those 46, like grain, acquirement, oilseed, things like that. So each one of these is the answer that we see here as far as the train labels. But what we need to do is, again, 1s and 0s are here. And so what we're doing here is we are getting the 46 elements. And in this case, for the answer for the thing that we're training, we know 100% that the answer on this one is going to be 0, 1, 2, 3 on the 3rd spot. Okay? So that's part of the setup, converting things to numbers, converting things into floating points, and then setting up the layers. And here it is. Okay? So I have, 64. I'm going to start here with this input shape right over here. I'm going to start here with 10,000 elements, whether that word is in the article or not. And then I'm going to use a ReLU to 64. What's up with 64? Well, 64 is going to be meant for the inner layer. So from 10,000, all the way down, I come with sound effects, by the way. From 10,000 all the way down to 64. This is called a dimensionality reduction. At first, I'm starting off with like 10,000 columns. But all I want here is the salient information, not the entire 10,000 words. We're not evaluating that, but just the salient information. It's kind of like facial recognition, right? Facial recognition is, what's the distance between your eyes and your nose, not whether if you have a zit here or not, right? That's getting too specific. Same sort of thing here. We just want the information that we're looking for. And then finally, after the 2 layers, we're going to get a softmax from it. Okay. So here's the compilation. And what we're doing is we're compiling the model. Now, models in machine learning, and particularly in Python, these are objects. And very much like, for all of you who do Java, you have like member variables inside of your class. You have a particular state that's running. Same sort of thing is happening here. All right, so I'm going to skip ahead a little bit so that way I can jump into the Kafka stuff. But one of the things that we're doing here is we're running this through a few times. This is called a model fit, and we're running this through 20 epochs. By the way, American English says epoch is epic. I don't know if you knew that or not. I've been calling it epoch for like a long time. And I found out like, wait, American English is epic? What's going on there? So the British will, or any language that's derived from the British language, will call it epoch. Anyway, this just means number of turns in this case. So what we're doing is we're running through this network 20 times to see if we get good at it. And here it is. Now, over here is the plot of the performance. So what we see here is after like 10 tries, 10 epochs here, we're not doing any better. We're getting as good as we're going to get. Training does particularly well, and in fact, the loss here, which is something that we want as low as possible, is great with training. But this is kind of like us learning in that book, right? In that science book or that physics book or that math book. Hey, I'm going to get good at the problems inside the book because I already knew the answer, right? And so mentally, I'm able to solve that problem easily. But if you give me, something that I've never seen before, I'm probably not going to do that great. So machines then, like humans, can only go so far. And so let's say we want to chop that down to 10. And here's the accuracy. Anyway, the point I want to make is, that's what the data scientist is going to undertake. They are using a particular notebook. So how do we productionalize this? So that way we can come out to Kafka and start to give it information. Well, for one thing I want to show you here is the prediction. So this one I'm giving it one particular article here. It's called X test. I'm giving it the 10th one. I'm plucking that out and running it through this machine learning model. And here comes the 46 different elements and the probability that it'll be one of those elements. So in this case, I'm using something called argmax, which is out of all these probabilities, find me the biggest one and then get me the index for it. And whatever that index is likely going to be the classification that I want to use. Okay? Now, where the magic is right over here. So the data scientist will save the model, or you can make it a part of the CI/CD pipeline. You could take a notebook and you could use nb-convert in the command line, or you can use that in a notebook, and you can convert a notebook into a Python script, and you can have your CI/CD do that. But here it is, and here's the save model. So we're saving the model, but we're also versioning it by using a timestamp. Okay? And TensorFlow will have this TensorFlow save model, save that particular model in this particular directory, and save that particular signature. Okay? Now, let's see over here. Let me take a look here. Let's see, I'm going to stand by. Machine learning data pipelines, and I'll make this one big. There we go. All right. So as an example of what this will do, I'm going to go over here to Notebook, and I'm going to go to this Reuters model directory, and as we see over here, I have a bunch of dates and times. Those are the versions for that particular model. Okay, and in them, they're just like serialized versions of your TensorFlow model. Now, I'm going to go to the lab portion in here. Again, I usually do this as a big full-day workshop, but let me just give you the better parts of this. I think what I want to do, I'll start with this one. So TensorFlow serving, you could just, once you have that serialized model, what you can do then is run a Docker container. And the Docker container comes from, here it is, TensorFlow serving. And the only thing you need to do is get that serialized model, put that into a Docker container. And there you got it. You got like your microservice for determining probabilities. So you can make a post call very much like this. Okay. Here's the version. You could predict it, give it some JSON data, something that it recognizes. Fill that in, and then it will give you the probabilities afterwards, okay? So once you have that web service, you're halfway there, okay? All right. What does that input look like? Let's go over here, and let's do a bat. I don't know if you know about bat. Bat is like cat, but it has lines and colors. I don't even know if it's going to look good. Yeah, it's going to look great. Look at that. So here's what here's not what bat looks like, but here's what the JSON looks like. I hit that particular web service, and what that's going to do is it's going to return another JSON with those particular probabilities. All right. So I'm going to skip a few slides here, but all this information is there, and what I'm going to do, I just gave you the demo for the machine learning stuff. So let's go next to Kafka Streams. So Kafka Streams, again, is consumer producer. So let's say like a credit card application. Someone fills in a credit card application on your Spring Boot app and fills that in, submits that. That goes immediately to Kafka, where it's going to be held there. If you want that into a permanent database, you could use Kafka Connect to take that message and dump that into the database. But for that real-time data processing, that real-time fast ETL that you want to do, you can do the following. So one of the more powerful things with Kafka Streams is that you can take a message and filter it. And maybe I want like some high value orders. So if that order is being able to be maintained, then, well, let me restate that. If an order doesn't meet my expectations, like for a high value order, I'm looking for something greater than 10,000, then that's not going to make it. But let's say this one, like I have Ohio 20,000. Here we go. Woo! Is the value greater than 10,000? Yeah, let's do it. And we're going to put this into another topic. Right? That's a simple streaming that you can do. You could also do a group by for this in streaming. So I can accumulate something and I could put that elsewhere. So if I bring in Ohio 100, for example, I'll do a group by state, and I'll do a accumulation for this, an accumulated sum of this. That so far from Ohio, I've gotten 100. Let's say from this Ohio 100, I change the color here. Different message. This is the running total for the state of Ohio. That's why I colored that a little bit differently. So I want to take that Ohio and I want to plug that in here into a different topic. So lots of things that you can do with the Kafka streams. Here comes New York 20. Again, group by, there it is. Running total is New York 20. New message coming from this is the representation of that, and I'm going to put that over to a new topic. Let's say New York 60 is coming by. Group by state, New York. And I want the running total. So 60 plus 20 is 80. So the current running total now is 80. Okay. Now, this is stateful streaming here. So one of the things that you could do with stateful streaming is you can get rid of all the old data and just keep the newest data. This is called compaction. But everything about this state, in fact, everything about Kafka, they are obsessive about fault tolerance to an extreme level. So, all this information is going to be backed up. And if you remember from that original diagram that when it comes to Kafka and everything Kafka-based, if I bring a message into a particular broker and then I'm going to use a stream to transform that, to do something with that and call my TensorFlow or whatever it is I want, post that back into a different topic. Everything is going to be backed up as well, so I have fault tolerance. If any one of the stream processes goes down, then another one can pick up from where we left off, okay? And that's the idea of like what a streaming is. And again, if you recall, once anything is into a particular topic, once they arrive in there, then you can post that over to a database. Okay. Well, let me come back over here and let me finish the rest of the story here when it comes to the model. Because let's say I want to deploy this onto Kubernetes or something like that. So what I have here is creating the container for the model officially. I'm starting off with TensorFlow serving. I'm moving that model as a file over to a particular location. And once there, I'm going to do a commit under a particular name and Reuters model. And I'm going to go ahead and upload that to Docker Hub. I'm going to do a Docker login. I'm going to do a push. And then I am good to go, okay? And so that's what I did. And if you take a look over here, I'm going to go to my K9s. Here's K9s, and I already have some information here inside of my Kubernetes. And one of the things that you'll see here is I deployed this Reuters model deployment. And it is hosted at 8501. If I take a look at the logs, you can see here everything is being hosted. And right there at the bottom, you'll see localhost 8501. That's good to go. And if you take a look at and here I'll highlight it for you. Ooh. There it is. If you take a look over here at the right-hand side, we have Reuters model version 1677, blah, blah, blah. That is the version for that particular model. That is being hosted at 8501. Okay, so I have that hosted. Let's take a look at some of the other players here. So I have Kafka. Again, that's my pub sub. That's where all the messages are going to be going. I have Zookeeper's a part of it, just to maintain the metadata for Kafka. And here I have the stream processor. Okay. And here it is, okay? It's just waiting. It's an application. Kafka streams are just, public static void main. That's it, with some extra programming, of course. But it's not like Spark where you have to deploy your framework first and have driver nodes and all these other things. The simplicity of Kafka streams is great. It's just, I'm going to run an application in whatever platform you need to. So that's what this one's doing. It's just waiting there, waiting for information to come into a topic. The moment it does, I'm going to go ahead and consume that, and I'm going to go ahead and call the service for Reuters. I have Redis here, and this one's just for a key value store. I'm using it for two different purposes. One is the articles. The articles are in English, right? So the word "the" has a corresponding number. So, I need to know what that number is, so I can convert that. So if someone is going to submit an article, I need to convert that "the" into the number 5. And, I need a dictionary for that. So I'll take that dictionary and put that into Redis as a local store. And what else am I going to do? The categories as well. What's a corresponding number with the category, which is the answer or the thing that I want to categorize at the end, okay? So those are all the different parts here. Now, how is this going to look when we run it? Well, I'm going to come over in here and let's see if I could do it. Let's see. There's Notebook. And here, let me come in over here. Nothing like live demos to really just get the old ticker moving here. Let's see. I am going to run this exec here. I've already created the topic, so everything should be in motion, and let's hope everything works. So I'm going to run the client here, and on this one, I already did one run before. I'm going to run 2 Kafka clients, and there we go. And I'll go ahead and increase the font here. And I'm going to go ahead and increase the font here as well. On this side, what I'm going to do is I'm just going to freak out. Let's go ahead and get this one over here. I am going to, I know where I have this. Stand by. I had already prepped this here with some articles. So let's give it a try. All right, there we go. Okay, so here's the consumer. I think, that's already running. And I'm going to get the producer over on this side. Ooh, it already did one. Let's see. I'm going to call it producer, and there it is. And I'm going to grab one of these articles here. Oh, didn't like that one. Oh, no key found, and it just bailed on me. No. All right, here we go. One more time. And I'm going to get this one here, and I'm going to bring it in. All right, there we go. I got this one today from New York Times. Mr. Belmer, an industrial mechanic, got another job at GM Transmission Factory in Toledo, etc. So let's see what this one is going to come in. An requirement. Okay, ACQ came in with that one. I did one earlier to prep for this presentation. That one came in as oilseed. But what we're seeing here is I am producing information. That's going into Kafka. The stream is taking the information from Kafka. I am negotiating with TensorFlow. TensorFlow is giving me the classification, and I'm taking that and I'm posting that onto a different topic. Now, with the time remaining, let me just describe a couple of items that I didn't have quite a bit of time for. But there's something called KSQLDB. The great thing about KSQLDB is that it's streaming, but you don't have to do any kind of programming like Java, Scala-based programming. You could just jump right in and do SQL code. Now, the benefit for doing something like that is the following. Well, one, you have the select. But one of the more powerful things about doing KSQL, and by the way, there are 2 different versions of the way that you can do queries. One's called a persistent, which means that at the end of a select statement, whatever the results of that are, I can post that over to a different topic. Non-persistent is just a straight select that you're just going to see on the command line. That's what this slide is about. But really the good stuff, or one of the really great things, is that you can create a UDF, a user-defined function. And that's just Java code. Now, why would I want to do that? Well, that's your tie-in, because what you could do is you could create a UDF for negotiating with TensorFlow and bringing the answer back down. And you just treat that like a SQL statement. That's fun. Okay? So here's an example of one that was using it with H2O. I put the source here just to give you an idea of what that should look like. But take a look how awesome that is. That's just SQL code. So you can create a stream process like this and say car ID, event ID, get me the anomaly of whatever that is from car sensor, and maybe the results of this, I can post this over to a different topic. So sweet. So I'll finish here with the following. The cycle completes, and I just, gave you a quick rundown of like all the different components of doing a pipeline with Kafka and TensorFlow. But the cycle has to continue. You release a model on Kubernetes or however or whatever platform that you would like, but the data scientist needs to know how are things going in production. Well, one of the things that you can do, and I'll finish with this one here, is use libraries like KSQL Python, in which they can sign in and then just query what's going on in Kafka and how things are moving along and how things are classified in real time. From that information, the data scientist can create better models, and then over to you again to do the ML ops to productionalize this data, okay? So everything within its place. All right, well, I'll leave it there. So what your team requires will determine where you'll need to operationalize your ML, depending where you're coming from. So, it's all about working together and having the quality tools that you need. All right? All right, well, I'll leave it there. Thank you very much, everyone.